Okay, so today I want to talk about an interesting combinatorial problem called Forbidden Configurations. So this problem has been studied by a number of years by various authors, and I just want to introduce some of the basic definitions and problems to give you a sense of kind of this fun subsection of combinatorics. So first, I have to start with some definitions. So I first want to define what a configuration is. What does it mean when I talk about forbidden configurations or even a configuration at all? So this is our first definition. Is configuration. So basically, we say that some 0, 1 matrix F, or 0, 1 matrix F, meaning that F only has zeros and ones, is a configuration of another 0, 1 matrix that we'll call A. Basically, if we can find some submatrix of A, which is a row or column permutation of F, so which is if it is a row column permutation of a submatrix of A. Okay, so this is kind of like a crucial definition that we'll be using again and again, so I want to just give some examples to make it really clear. So maybe the first example is if we take I2, just the 2 by 2 identity matrix, we call this F, and then we have some matrix A, maybe it looks like something like this. Then F is a configuration of A, or we say A has a F as a configuration, because you could take, for example, the submatrix along these 4 elements, and you have the identity. And it could also be a row and column permutation. So, for example, we label that matrix A, and had something here. We could also we could have any number of configurations, and it could be row and column permutation. So this could be a 1, this could be a 0, for example. And that's just like a row column permutation of F. So in all these cases, A has F as a configuration. Sometimes we denote this as this to say A has F as a configuration. Okay, so now that we've defined configuration, we can define kind of the next important thing. So one more just basic definition is we call a matrix simple if it is a 0, 1 matrix and it has no repeated columns. So a matrix A is simple if it is a 0, 1 matrix with no repeated columns. So, for example, this matrix that I have here is not simple because the 0, 0, 0 column is repeated twice. If I replace one of these by 1, then this matrix is indeed simple. What simple lets us introduce is the next important piece of notation, which is something we call a void. So we have a void.
Oh, wait, sorry, question. So we don't care about rows, like repetition of rows?
That's right. So you could have repetition of rows. So this is a simple matrix, even though there's 2 repeated 1, 0, 0 rows.
Sure.
So yeah, so we only care about columns and whether I is 1, 0. That's right. Okay, so we introduced this avoid MF, which is really just a fancy set. So it's this is the set of all m road simple matrices though with no configuration F. In some sense, some matrix is an avoid MF if it avoids this like configuration. So if this is if this is the thing we're trying to avoid, we can find no submatrix in A that's a row or column permutation of this. That's why it's kind of suggestively named avoid. We are avoiding this smaller matrix F. So so just kind of keeping along with this example, if we have something like this, then we could say that in this case A is in a void 3 because A has 3 rows, and I2 because F is I2. So in this case, you can see regardless of whatever 2 by 2 submatrix we take, we can never get the identity, even if we do row or column permutations. Okay, great. So basically, yeah, I think that's right, yes. So, okay, the central problem we can finally introduce in forbidden configurations, which is finding this thing we call the forbidden number, which in some sense asks, how big can you make your matrix A while you still avoid some smaller submatrix F? So, how many columns can we add? How many, how big can this matrix get without becoming too big that we're forced to have some submatrix F? So this we formalize with the forbidden number, and we define the forbidden number is defined to be the maximum of all matrices A okay, and this is just the number of columns in A, so that's what I mean by the size of A. Okay, so what is this saying? We look at all the matrices that avoid the matrix we're trying to avoid F, and we look at the number of columns. These have to be simple, so we can't just like append the same column over and over again, right? Like we couldn't just add 1, 0, 0 repeatedly and make A arbitrarily big, because at most, basically your matrix A could have 2 to the m possible columns. You can't have any repetitions, so so you have like a bound there already, but oftentimes your forbidden number is much smaller than that 2 to the m, because you have to make sure you don't have any columns that kind of contain a certain submatrix. Right, and of course this depends heavily on the number of rows. If you get more rows, you can kind of create more columns that avoid matrices, and so often a critical question is kind of, as we increase the number of rows, how does the forbidden number change? Is it linear? As you increase the number of rows, can you add like a linear scale number of columns and so on? And this is kind of the central question: is what is the forbidden number for certain submatrices F? So I just want to run over a couple examples to kind of give an idea of what this forbidden number really means, and hopefully make clear some of the questions that are interesting to look at. Okay, so first a very simple example. So let's say I wanted to find, maybe go over here. Let's say I wanted to find the forbidden number on two rows. So for the number of 2 rows of just the simple matrix 1, 1. Okay, so what is this? Just to be very concrete, I mean, you can just think about it just by hand. You could add, okay, adding a 0 column, or we can only have two rows. Okay. We can add a column with zeros. We can add any column with 1, 1. And we could add, and then basically we're done, right? The only other column that could be unique from these ones with 2 rows is 1, 1. We have to avoid 1, 1. So that's as big as we can get. And that exists. So we have the forbidden number on 2 of 1, 1 equals 3. And it's there. I mean, then we could look at what happens if we let another row in, forbidden number on 3 rows of the same matrix. Okay, it's like the same exercise, right? We can add a 0 column and any column with 1, 1s. So 1, 0, 0, 0, 1, 0, 0, 0, 1. Any other column we have would have 2 1s, even if it's like this. We have some submatrix just by taking these, and we've basically hit the matrix we're trying to avoid. So again, this is the best we can do. We can only have 1, and so this is 4. And you can see in general, if we have m rows, the forbidden number of this matrix is m plus 1. M because we have m choose 1 ways to have a column with exactly 1, 1, and then is all 0 row. So there's like a very simple example to just give an idea of what kind of solving one of these small matrices look like. Okay, maybe to return to the case with the identity matrix, just like I2, we could say, maybe we can kind of play the same game. So if we want to find the forbidden number with on m rows of I2, what is this? So kind of we can think basically, first of all, we can make a construction, right? Because if we can find a matrix of some size that avoids I2 on m rows, we know that gives us a lower bound right away. And if we can't make anything bigger, that's the forbidden number. So okay, so we can first construct something to like get a lower bound, right? So we could have like a 0 column, and we could have a column with 1, 1 at the top, 2 1s, and 0s, 3 1s, and kind of creating this like upper triangular matrix, and so on, all the way until we get a column of all 1s. Okay, so this basically has m plus 2, or right, sorry, m plus 1 total columns. And we can't do any better. If we were trying to do better than this, there are m columns of A. So for example, if we thought forbidden number was m plus 2 or larger, then there would be m columns in our matrix that have both 1s and 0s. And basically by the pigeonhole principle, at least 2 of these columns contain the same number of 1s. And so, because remember we're restricted to 0, 1 matrices only, because the columns must be unique, we would have to have one spot where there's a 0 and 1, and then somewhere else where there's 1 and 0, and we have I2 basically. So, so that's just another example. So these all kind of scale linearly with the number of rows we allow in our matrix. Okay, so there's some interesting examples, and there's a number of theorems that kind of relate, that sort of classify these matrices. Sometimes we look at multiple copies of I2, so if you have, if you're trying to avoid a matrix, because this matrix that you're trying to avoid doesn't need to be simple, but you might try to avoid like multiple copies of I2, you might try to do all sorts of matrices, and so there's been a lot of work to basically classify these matrices, provide bounds or exact solutions, and that's kind of what forbidden configurations is all about. So instead of going through all of those examples, I also want to talk about why this might be kind of interesting, like what is this forbidden number, like what does it really tell us anything about anything if we know the forbidden number of the identity on 2 rows is m plus 1, like does that mean anything? And one thing that's kind of interesting is we can actually connect all of this to graphs, to hypergraphs. So whenever we have a simple 0, 1 matrix, we can think of this as an m by n matrix, so there's m rows, n columns. Then we can think of each of these as m vertices, and each of the n columns as an edge. So it's a hyperedge, we have to have a hypergraph. So this is basically just the characteristic vector of the vertices included in the hyperedge. And so a lot of these problems can be related to graph theory in this way, and in other ways. And so kind of we create this connection to graph theory in other areas of combinatorics. And so in that way, some of these results can have interesting implications elsewhere, and results elsewhere can have interesting implications here. And it kind of ties everything.
Can you explain to some people what hypergraph is?
Oh yeah, absolutely. So a hypergraph is like a normal graph you're used to. So it has vertices and edges. So maybe an example helps. So maybe we have like 4 vertices, except this time, instead of the edges just being between 2 vertices, something that looks like this, we kind of expand our idea or abstract our idea of what an edge is to connect any number of vertices. So we might have an edge that somehow connects all 3 of these vertices. So like this is somehow an edge, and then maybe somehow this is like another edge. So we can basically connect an arbitrary number of vertices all together with one edge instead of just 2. That's what we need, and so maybe I'll make an example for how a matrix would connect to a hypergraph if, for example, we had something like this, a 3-row matrix that looks like this. Then we have 3 vertices because we have 3 rows. Maybe we'll label this like this one corresponds to V1, V2, and V3. Here is V1, V2, and V3. In this case, our edge V1 is just kind of trivial, it just includes V1, and the next one we include V1 and V2, and our last edge includes all 3. So we kind of have 3 edges like that. So that's an example of how we might translate one of these simple 0-1 matrices to a hypergraph, and kind of suggest how we might think about avoiding certain edges and certain, it might correspond to kind of avoiding certain sub-matrices as well. So there's, connections there, and you can kind of generalize the problem in other interesting ways too. What happens if you draw the assumption of having only 0s and 1 in the matrix, and so on. So that's kind of the basic idea, though. It's kind of fun. It feels like solving a puzzle, and I just wanted to introduce this kind of fun little piece of combinatorics that is, I think, pretty interesting. So.
Oh, thank you. Also, I guess a question would be like, so what's known about it? Like, are there any nice bounds that people already discovered?
Yeah. So a lot of what's known is, for example, specific matrices, but you can actually run into like matrices that are pretty small that people don't know about in general. But yeah, often they're bounds. Sometimes there's like sets of matrices that are known to have like that are known to be like O of m squared, for example. So they are basically scale quadratically with the number of rows. And so for a lot of matrices, these either exact or forbidden numbers or bounds on forbidden numbers are known. But yeah, there's still matrices where it's not known in particular once we draw some of these assumptions. Once we let there be more than just 0 and 1, for example, then it kind of, the problem becomes complexified and there's a lot less known. So.
And what kind of techniques are used for that?
Yeah, right. So so some of the simpler ones like this one, you can kind of just explicitly construct matrices, and then maybe you just kind of either apply some inductive technique or something to find an exact forbidden number. A lot of techniques, like the connection to graphs is another very common technique. Sometimes you can connect it to like tournaments on graphs and so on, and so that's another common technique, kind of applying tools of graph theory to what we have here. And then sometimes you can kind of break down the problem. So there's some bounds that kind of, if you're trying to find the forbidden number of a larger, more complex matrix, you can kind of break down that larger, more complex matrix into kind of components, and then based on each of those components, you can know the bound on the components, and that tells you something about the bound on them all together. So for example, if you were trying to find the bound on like 0, 1, 1, 0, 0, 1, 1, 0, just like repeating the identity multiple times, you can kind of like break this up into multiple identities. We know the forbidden number on I2, and there's like theorems that help you combine that together to give you a bound on this one. So yeah, so those are some techniques that are used.
Can you use like help of computer, like some computational power to prove some bounds?
You can, but it gets to be very tricky very fast, right? Because you have to consider, like the definition of the forbidden number is like the maximum matrix and everything that avoids. And so checking if a matrix, if, for example, a matrix does avoid some other smaller matrix is fairly difficult, and then iterating over like all possible matrices can be pretty difficult too. But there are ways where computation can help, and you can kind of get an idea. Like, okay, do you think the scale is like roughly like this, or Yeah, and sometimes like once we've simplified the problem too, or we have additional constraints, then computing becomes more feasible, and we can kind of get an idea on there too. So,
Gotcha.
yeah.
How many?
Yeah, or compute the forbidden number up to like a relatively large number m, and see how it scales up until m equals something big.
That's such a big problem. I love it. It's like so nice.
Yeah, it feels like just working on like a puzzle all the time, so it's pretty fun.
It's like one of those like very pleasant problems to work with.
Yeah, I agree. It's like something like you might do for fun when you're like traveling or something. Like it's like a Sudoku grid or something almost. You're like trying to find out how big of a matrix you can make going on.